Morena koutou. Welcome to the first session of day 2. My name is Eryn and I will be chairing this session. In this session, there are a total of 3 presentations, and I hope most of us are quite familiar with the format by now, but each presentation is 20 minutes long, hopefully 15 minutes soft talk and 5 minutes for question and answer. During the presentation, if you have any questions for the speaker, please feel free to pop them on the live Q&A portal, and we will go through as much as we can in the 5 minutes until we change over to the next speaker. Today's session is workflow and meta-analysis, and I'm very curious to hear those. So without further ado, I'll bring on our first speaker, Dr. Alexander Pletzer.
Thank you, Eryn. Kia ora, morena, tēnā koutou katoe, ko Alex Pletzer, toku ingoa. So it's a pleasure to be back at NZRSE. This is probably the 5th or 6th, 7th attendance to the conference. It's always nice to see all the familiar faces and new faces as well. Today, I would like to talk a little bit about 2 things, workflows and optimization. And I think the motivation behind that talk comes from the fact that since last year, at least as far as I'm concerned, workflows have become much more prominent in my work. And so it's perhaps something that could be of interest to a certain number of people. I have also heard, the word workflow pronounced several times yesterday. I know that Eryn, for instance, in her research with her colleagues, is using a workflow. It's called SnakeMake. But I heard the word also in the case of Olivia Angelin Bonnet yesterday, who talked about good software development practices, and she mentioned targets, which is R-based workflow manager. Yesterday again, Simon Pletzer, for instance, talked about Hydra, and I think there's a certain connection between what he presented yesterday and workflows in general. So this is something that I'm presenting with Maxime Rio and Chris Scott. We all working for NZRSE, some at Neal in Wellington and some at the University of Auckland. But it's also motivated by some work that we've been doing for Neal people in hydrology. So let's go. So the motivation is a code called SWOT, which is a legacy code for modeling hydrology. You don't need to know all the details about the code. I think it suffices to know that it's a legacy code, so it's typically not something that is running in parallel, but it does take quite a bit of time to run. Here on the right-hand side, I'm showing a picture of the Hauraki Gulf catchment region around Auckland and the Bay, and the model, what it tries to do is sort of tracking the concentration of pollutants or water or other things that sort of flow down the rivers. I'm not an expert of hydrology, so may not be able to answer a lot of questions about hydrology, but the motivation is a legacy code that typically runs on a laptop and sometimes for a very, very long time. You can see from the catchment basin that things can get quite complex. In addition, we have to keep in mind that you have different kinds of models. You have land use, slope is taken into account, the soil quality, and as well as the topology of the river system. So the problem is need to go faster. That's because it can take maybe 5 minutes in the best cases to run the code, but sometimes it can take longer, up to 3/4 of an hour. On top of that, we need to run the model thousands of times for calibration, perhaps optimization, emulator training, and altogether, perhaps 10,000 runs would need to be taken, and these could take thousands of hours, and that's equivalent to 40 days if we were to run serially. So it is time at that point to bring the big iron and to run in parallel. We have made attempts, and the team at NIWA has made attempts to run things in parallel in multiple ways, and those the various approaches that were taken in the past and how they performed in terms of their speed up, which varies. So on the left-hand side, there's a software called SWAT Run R, which sits on top of the SWAT Fortran code. It's R code that can be used, for calibration, and can exploit multiple workers. But it is based on shared memory parallelism, and unfortunately the maximum speed up attained with this approach was about 10 times. So maybe you're going down from 40 days to 4 days, which is still a very long time. Now, on the right-hand side, the extreme right, we also looked at RSWAT, which is a sort of similar approach, but it involves setting up a R cluster, and which is based on the shared memory again, but it does scale a little bit better. Here we have a 16x speed up. I think we've been able to reach something like 20. But again, this is going to be limited by the number of cores you have in a node on the high performance computing platform. So on Mahuika, for instance, we have 36 cores maximum. We have more cores on the newer platform, which is Milan, where we can go up to 128. But nevertheless, this approach seems to be limited to a speed up of about 20 max. Another approach, which is the one in the middle, and turned out to be perhaps the most successful so far, is to run all these jobs in parallel. So essentially, if you want to figure out, how much flow will go through a river at a certain time, you run under certain different parameter choices with different parameter choices, and then you can create some statistics, and that's what we did. We exploiting essentially the fact that each run is embarrassingly parallel, does not depend in any way on any other run, except in its final stage where you have to create or build some statistics. We used job array, which is through Slurm. It's basically the default sort of basic workflow management system that comes with Slurm. And we were able to get 44x in that particular case. But as you can see from the slope increases. So on the horizontal axis, we have the number of workers, which essentially is a proxy for the amount of resources that we're asking for. But the fact that the slope is quite positive means that we could, in principle, go higher. And so that was quite encouraging. So now Silk comes in. Silk is a workflow engine developed at NIWA, which I think has some interesting features that perhaps not every other workflow system has. And these features perhaps will allow us to do things that we were not able to do with up to now, or perhaps with some other workflows. So like many workflows, there are things that you can do, such as running sequentially. So I have here a couple of cartoons. The vertical axis goes down, it's time. So you have, in the sequential case, you run a task A followed by a task B. This is a basic building block. You can assemble these building blocks to build something quite complicated if you wanted. But you can also run things concurrently. So you have A and B running at the same time. And these can be Slurm jobs by themselves, so they can be submitted, and the workflow management system would be able to track, and figure out when task A and B have completed the execution, and in order to move forward to the next task. So A and B concurrent, that's one possibility. You can also have a gather pattern where you have A and B running together at the same time, but C depends on these two. Or you could also have a scatter kind of a pattern where you have A that feeds into B and C, and B and C can then be run concurrently, but only once A has finished. Also quite interesting. So all these patterns, basic patterns which I just described, are fairly well supported by any workflow management system. However, the last one is sort of an interesting one. Imagine that you're running models, a bunch of models, so 10 models in this particular case, and you just choose the fastest one. So as soon as one of the model finishes, you take the results and you're done, and you kill the other tasks. That is something that you can do with Silk. The other thing that you can do with Silk is you can cycle. And Silk, the term Silk comes from cycling in some sense, although it's pronounced as silk, like the fabric. The idea here is that you repeat tasks until something is happening. And this is, of course, a basic building block which could allow you to do genetic optimization. So imagine that you're starting with some random initialization of a population, and then you test their fitness. So you have a fitness module, and then from that you select and breed a new population. After which point you go back to that cycle, which is fitness, select breed, fitness, select breed, and so on and so forth. And that cycling can go on forever, potentially. But you can typically you would sort of stop after some time, once the fitness of your solution is good enough. So so how does that fit with parallelism? Well, there are a couple of tasks that can be run in parallel, and let's just concentrate to the right-hand side, on the right-hand side of the diagram here. So essentially, the random initialization can all be performed simultaneously. So in this particular case, we have 5 random initializations. Once the population, a certain population has been initialized, then you can estimate its fitness, which is, imagine a cost function. And, it's something that returns a scalar value, and the higher the scalar value, the fitter a certain individual is for that particular population. That again can be run in parallel. And you have, but then finally you have to select and breed. And in order to perform this particular step, you need to bring in all these populations together and select maybe the 20 or 30% fittest population before continuing again with another cycle: fitness, select breed, fitness, select breed, and so on and so forth, until you reach a certain level of fitness. What's interesting now is that this complicated diagram, you would think that, oh my God, it would be so difficult to represent, all these arrows. But actually, in the language of Silk, all it takes are the few lines that I'm showing on the left-hand side. And what they say is that at the top you have m equals 0 to 5. This is sort of the level of parallelization. For simplicity, we only have five workers, 0 to 4. And then we start with clear. That's R1 means runs once. Clear, then random initialization and fitness, and then P1 means that is something that you just run periodically. And the previous iteration of select breed at minus P1 feeds into fitnesses. This is a family of fitness evaluation. But the other thing that was sort of critical here is that we're going to check the output of whether fitnesses or the family of fitness calls actually fails or succeed, right? And that will then either feed back to select breed. So if there's a failure, that means we haven't reached the fitness that we wanted. Then we still want to select and breed. Otherwise, we stop, and then we can do some plotting, or we can do various other things. So So this is basically how it would go. You know, you start with a certain population, and we could see essentially what we did here. We used a cost function that had a lot of minima. Let me just run that again, and eventually the absolute minimum is found by using a genetic algorithm. Okay, next slide. Okay, so so I'm down to the summary at this point. So optimization can be numerically very costly. Time is expensive, but computing is cheap and becoming cheaper. So so the idea would be to run as many jobs as possible in parallel. In this proof of concept, we only ran 5 instances, but we can imagine running thousands of instances. So it's not always easy to parallelize a legacy code, and a workflow is something that will allow you to exploit parallelization without actually changing the code. We choose the optimization method. Well, the optimization method has to be suitable for a massively parallel approach. So evolutionary population-based optimization could be a way forward. You know, some of the workflows are slurm aware, so it's nice to be able to do that. We could remove the communication barrier. That's something further work could be performed on was spent on removing that communication barrier. As you can see here from the top, I mean, basically we have to wait for the fitness to finish in order to select the breed, but sometimes these calculations can take longer or shorter time. And so we could have an observer that periodically polls the workflow and uses the fitness values available so far to select and breed the next generation. So a workflow, in order to be used in that particular application, would need to be able to loop or cycle and support additional conditional dependencies. So the output, sort of success or failure of a certain module would trigger different tasks. So this was just a proof of principle demonstrating how Silk could optimize a problem. So do you need any help with workflows? So maybe you are not aware, but NZRSE has a consultancy service, and researchers from this institution, University of Auckland, NIWA, University of Otago, Manaki Whenua, are in principle eligible for a free NZRSE consultancy, provided there are enough hours for that depth. So please talk to us, send us a message to support.nzrse.org.nz if you're interested. Keep in mind that we're not only doing workflow implementations, but anything that has to do with performance improvement, software development, technical expertise, visualization, software, sustainability, data science, areas that we're active in. And please check out other talks about workflow in particular. I think at 1:40, Maxime Rio is going to talk about his experience in developing the fMRI workflow Eryn mentioned yesterday. Thank you.
Kia ora. Thank you very much for that, Alexander. I can definitely recommend the consultancy. We have enjoyed it very much from Mātai, and I'm looking forward to actually rolling it. If you have a question for Alex, I think we have a time for like a 1 or 2. I can't see any questions popping up right now, but now's your time. I might sneak in my question. Alex, you're aware of the SnakeMake workflow that Mātai has been working on. And we've been discussing about like 100 cases and stuff to process through. And we're looking into potentially importing about 1,000 cases. But those are not a cyclical process. It has a very definite start to end. Do you think it might benefit from Silk?
I think either workflow management systems would work. So I would probably stick to SnakeMake because you're mostly familiar with. So SnakeMake is file-based. Silk is task-based. They both could be used in that particular instances, but if your inputs are files and your outputs are files, then SnakeMake is a good way to go. And I think it's definitely some, a good tool that has a lot of support at NZRSE as well.
Cool. Thank you very much. Well, so we can keep to the lunch hours. Maybe we'll move on to the next speaker. And if you have any questions further for Alex for his presentation, please feel free to reach out to him during the conference. Cool. So we have a next speaker, Dr. Arindam Basu, talking about meta-analysis package in Julia. So Arindam, whenever you're ready, please feel free to start.
Hi, hello. Yes, good morning. My name is Arindam Basu, and I'm from the University of Canterbury, and I'm here to present today a meta-analysis package that I have written in Julia and some of the lessons that I've learned in the process and what do we need about it. And so this is where this is the objective of my talk. Here, essentially, in this presentation, I'm going to talk a very little bit about meta-analysis, just barely an introduction. I'm going to talk a little bit about Julia and what was the motivation to build the tool for conducting meta-analysis in Julia, and a few things about the research software engineering that I learned about meta-analysis and using it with Julia, and what needs to be improved, the next steps, some of the lessons that I've learned, and so on and so forth. So to begin with, what is meta-analysis and why did I choose to make one in Julia? Now, I am an epidemiologist, and for my work, I have to rely a lot on the work of other people. So, which means that people who have done primary studies and then and other meta-analysis and reviews of other people's work, and those are very, very important for my line of work, to look at other people's primary studies and then synthesize them. And there has been an increase in the trends in the papers with the term meta-analysis in the titles, as you can see. Basically, what this is a process of evidence synthesis. So every primary paper has got information about the participants and the exposure that people use in order to test their hypothesis, the outcomes that they test, the measures they obtain. And it is not just a matter of health sciences where I work, or epidemiology or environmental health and others, but meta-analysis is also popular in other fields. So in economics, in engineering, in environmental sciences. The idea is this, that we pool the results of different studies together, and as more and more studies are being conducted, then it becomes important that we have a way of pooling the results together in many ways. So after pooling the results, people obtain a summary point estimate, and then they build a variance around that point estimate. And then if there are other variables that are present in the in each of these studies, then these studies allow us to do what is called meta-regression. So if there is a y variable, then we would like to see what are the other variables that can enable explaining the variations around the y estimate that we observe. And so, as you can see that, if you take like 5-year or decadal, 5-year intervals, or even for a decade, you can see that there is almost like an exponential growth in the number of studies that are basically meta-analysis. Another class of studies that are very close to meta-analysis are systematic reviews. What systematic reviews do is very similar to meta-analysis, except that do not statistically pool or weight the studies together. So that's where meta-analysis kind of differs from a systematic review. Otherwise, a review with a statistics built into it is what is meta-analysis. So basically, meta-analysis goes through a series of steps that are reproducible. So you start with a protocol of a study, then you start with a question, which is called a PICO question. PICO stands for participants, or the pieces that are important, or units of the analysis, intervention or exposure, or if you are doing an experimental setup, then what experiments are being conducted. Comparators, in case of health sciences, healthcare, medicine, we talk in terms of either placebos or alternative medicines, and outcomes are very specific outcomes that we want to study. Then we search various literature databases. In case of medicine and health, public health, we study PubMed or Ovid, Medline, and so on and so forth. And then we scan the titles and the abstracts, include, exclude, what studies we would like to include in the analysis based on what was written on the title and abstracts of each of these studies. And then for all the sets of studies that have their full text information available, we obtain the full text information, we abstract data from each of these individual studies, and then put it into a database. And then we conduct what is called a quality appraisal of each study, which means that we take a look at each study and then we study them, whether the studies were conducted properly, to answer these questions. And at that point, we do what is called a synthesis of the pooled effect estimate of each of the body of evidence. So let's say I take 10 studies, and each of these 10 study has got its own effect estimate. And a variance estimate, a variance around that effect estimate. Then I'm going to take the inverse of that variance, multiply the inverse of that variance with the effect estimate of an individual study, and that will call a weighted estimate. And then I sum up the weighted estimates to obtain what is called a pooled effect size. And that pooled effect size can be viewed in two ways. One, in which I conceptualize that the sets of studies that I have obtained are complete in themselves, or I can argue that these sets of studies that I have obtained, they are like a random distribution or a random sample of a distribution of like infinite such studies that are possible. So it's basically, then I calculate what is called a random effects estimate. And then I line up each of these studies based on their effect size and how they relate to the final effect that I want to study. And that is called a forest plot. It is obvious, it is inevitable that when we are conducting a study, we will not be able to obtain every possible study that was conducted on that topic. And obviously some studies will be missed. As long as the studies that are missed are not really small studies that have got negative findings in them, then it's okay. But if you miss those studies, then that open up to publication biases. And so we need to uncover this publication biases and either calculate it or show it graphically. And then for many different ways in which we can cut the data based on what subgroups of interventions were studied or what subgroups of individuals were studied. We can conduct a subgroup analysis, and then we perform what is called a meta regression, which means that if there is an outcome variable that has been measured in some uniform way, we'd like to see how the variability of that particular variable can vary based on what other variables were studied. So this is in a nutshell what is meant by what is conducted in a meta-analysis, and why meta-analysis are important. So with something like this, we know that there is a rich literature and software that are already available for meta-analysis. This process has been going on since 1973, and one of the most widely used package is the Cochrane Collaboration's RevMan package. It is now web-based, and it is very useful. In terms of free and open source software, for R, we've got packages such as Meta4, APR. If you go to CRAN Task View, you will be able to see many such software available. You can also perform meta-analysis in Stata using a very simple set of commands. Meta set ES stands for effect size, AC stands for standard error. And if you do that, then it is going to do your meta-analysis. Of course, the preliminary steps of selection of studies and abstraction of data from individual studies needs to be done by the researcher in the first place. And then once the researcher has got their sets of studies with the effect size and standard errors, this is going to spew out the results. But one of the things that's, I mean, this sets of procedures are not with every statistical software that we use these days, or not even with many of the numerical analysis software that we use. For example, there are no packages or modules, as far as I know, in Python that will help you to do meta-analysis. For example, in some other statistical software that people use, it is not possible to do meta-analysis. You can probably do meta-analysis in spreadsheets, but most people would do that in R. Now, I work in Julia a lot, and there was no package in Julia. So the idea was that you wanted to set up a very simple package in Julia that would enable us to do these very basic tasks in meta-analysis. And one of the most important tasks that needed to be done was to convert between various measures, because people report the effectiveness of their interventions in many different ways. So these have to be brought into a standardized format and then tested. Another thing that is very important is this, that if we believe that the studies form a random sample of a vast universe of studies, has to be some ways in which we could easy way to assess heterogeneity. We need to perform the fixed and random effects meta-analysis, as I explained before. Output forest plots. Publication bias is important, and this is usually examined using what is called a funnel plot, or there are other statistical ways of doing it. And of course, do a subgroup analysis and perform meta-regressions. Understandably, not everything that is involved in a meta-analysis can be done in a software, and that's often not being possible. However, there are add-ons that can be built into this software. So I took my my notes from a very good book by Michael Borenstein and colleagues. It's called Introduction to Meta-Analysis. This book is very comprehensive in the sense that it teaches, or it describes in great details how effect sizes can be converted from one end to another, how to do heterogeneity tests. It is a complete book on the theory and practice of meta-analysis. So what I wanted to do was to turn this particular book into a set of Julia codes. There is, of course, a corresponding set of codes from this book written by Julian Higgins and Rothstein and Hedges and Borenstein to perform meta-analysis in Excel spreadsheet. But my motivation was to do that in Julia. But you may want to know why Julia? Because Julia, in many senses, is a software that is meant for, or a programming language that is specifically meant for numerical computing, much like MATLAB. Now, there is no meta-analysis module, as far as I know, in MATLAB, and Julia is the syntax of Julia is very similar to MATLAB, and Julia is very fast. It's a language that is often referred to as a language that walks like Python and runs like C. It has got excellent graphing features using a package called Maki.jl, and there are many other plotting features that are available. It's a very, very fast language, and it is also quite easy to program and extend, as I will show you. And the syntax is very intuitive, so there is not much hassles. There's no issues with like leaving spaces. Writing a function is relatively straightforward. It's very scalable in the sense that you can increase the scope of the program as much as you can. It uses a concept called low-level virtual machine that really increases the speed of the execution of the programs. So, for many reasons, even though many other packages are available for many other statistical programming languages, for example, R, for instance, I thought that it'd be a good idea if we could have something for Julia, because none of these packages of doing a meta-analysis was available in Julia before. So the way to do that is that I used a Mac and a Linux machine to use this. We used a program called package build, and we stored the work in a folder called Julia .julia file folder. In the .julia folder, there is a subfolder called dev, which contains the code, the source codes for this. You can use any code editor that you like, such as NVim, Visual Studio Code, Pluto, Helix, and you can also use any plain text editor and use what is called a Julia REPL, which is like the read, eval, and loop. And then all you need to do is to define the functions and modules. And if you have a, we using modules, you can include the functions in the in those modules to build the package. And then this simple series of scripts will enable you to create some run tests folder where you can run the tests. And then it is very easy to deploy it to a Git repo of your choice. So which means that if you want, you can host it in something like Codeberg or GitLab or any other Git repository. But by default, they enable you to host it on GitHub. And then what happens is this, that they build a continuous integration system with the GitHub so that you can deploy any changes that get pushed upstream and gets run. And this simple system enables you to distribute over the entire Julia ecosystem once you register it with the Julia registrator packages. And when it comes to the end users, all end users need to do is to add meta-analysis package. It will pull it from the repository and it will run. So when the meta-analysis packages, various models are loaded, it is loaded using a function called using meta-analysis. So if you want to take a look at the meta-analysis package, the meta-analysis package lives in my GitHub repo called MetaAnalysis.jl. And then from there, it gets linked to the GitHub's repository, to Julia's systems. So there are a few dependencies that I used for this. So these are Karamaki, data frames, distributions. So Karamaki is a plotting package. Data frames is a package which enables you to use a data frame to define a set of studies in the form of creating a data frame. Think of it like data table. Distributions enables me to use the various distributions such as chi-squares distributions and others to evaluate the p-values. The generalized linear models is very useful for running the meta regressions, and the hypothesis tests are useful for testing the theories and the hypothesis. The keyword compatibility is compat is this, that at this stage it is compatible with Julia 1.9, but in future it will be compatible with higher versions of Julia. So when I change the metadata, I mentioned that it will be compatible with specific packages that I can. This system helps me to keep the code tidy and troubleshoot and make it specific to various different versions of the packages that I've used for this. I can leave it open-ended by removing the minor version changes. So for example, Julia 1.9 would make it compatible with 1.9 from 0 to all the way to 1.9. At the moment, it is 1.9.3. We could do that. And at the moment when I developed it in Julia 1.9.0. That's why I kept these compatibility layers, but I can change these things. So the way it works is this, that you write individual functions and then you export the individual functions. And once you have done that, then you include in the module, in the base module, all the different files that contain them. So for example, the converter.jl is a Julia file that helps to convert across the different effect sizes. The fixed effects.jl helps enables you to do what is called fixed effects meta-analysis. The forest plot generates the forest plots themselves, and so on. So the funnel plot generates the funnel plots, and so on. So what I'm going to do is show you a few of these formulae that I put in. So for example of a function where we use what is called a Hedges G estimation, which estimates the standardized mean difference after adjusting for the levels of their degrees of freedom. And you can see that it is a simple function. And what it does is this, that the function G in independent groups G estimation is the function. So, and that is represented here in that G independent groups. And there is a separate function that estimates the variance of the G for the independent groups. And so this is a motif that is used in order to build the Julia functions, the Julia package. So basically you write functions, you export it in the main module, and then what you do is include the various files. That's all is needed for setting up these functions, and you run the tests. This is another one. For example, how do you do fixed effects meta-analysis? You can see that the entire procedure does not take a lot of lines of codes to do this, and I can import other functions with it. So for example, with the distributions, I can import their CCDF functions, and that's quite useful. So ideally, the module name dot the name of the function should be written, but even if you do not, even if you omit it, as long as the as the program understands these ones, it can pick it up. So this is the, and you can see that the calculation of the fixed and random effects meta-analysis. This is the forest plot that gets generated. We use the forest plot using what is called Cairo-Mackey package. And again, it is a very flexible way in which the forest plot can be generated. And all the end user needs to do is to indicate the Y and the V. But there is the program leaves the possibility of fine tuning the forest plot to the user's own will. If you want to create a separate module or another way to create a forest plot, it is possible using the Cairo-Mackey package to extend the forest plot to include other variables and other features. And so that's one way of doing it.
Sorry,
Very similarly, one can create what is called funnel plot, and so on.
Sorry to interrupt you. Unfortunately, we ran out of the 20 minutes, and just to keep on track with the time,
okay,
we will probably move on with Mark's presentation now. However, if you have a question for Arindam, please feel free to put that on the question and answer. And hopefully we'll have some time at the end of Mark's talk to cover some
okay. Thank you. So I can stop share this?
Yes, please. Thank you very much for the talk, Arindam. I have some questions for you later.
Okay, sure.
Cool. Okay. So last one of this session. Thank you very much for staying around. Mark, Neal, I love your talk title. Please share your screen whenever you're ready.
Katoa, ko Mark Neal toko ingoa. Can you? I think you can see my screen now. Yep, great. Okay. Yeah, so moving into a new era with our modern science workflows. So first of all, a little bit about what is DairyNZ. So we are the research, development, extension, and advocacy that we provide to dairy farmers, and dairy farmers pay for that through a levy that they choose to pay. And so our mission is around delivering a better future for farmers, and science is a key part of solving problems. And so we have a lot of issues that we're working on any given day around productivity, footprint, sustainability, profitability, and our science is a key part of that. So linking back to ethics and responsible science, so we've got three different people here, and it might not be obvious what links them, but the person there on the left is Peter Singer, who's quite influential ethicist and philosopher. And in 1971, he wrote a very influential article which really kicked off the effective altruism movement. And that was triggered by some tragedy that was happening in what was East Pakistan at the time and Bangladesh now. And just to be clear that he wasn't making up everything that was entirely new, one of the things he did was quote work by St. Thomas Aquinas, who was obviously an older guy, Jesuit priest in the anyway, a long time ago. So yeah, so effective altruism is what links those pictures. And so if we're asking the question about, okay, what's our responsibility to others in the science space, we can leverage off some of that philosophical thinking. So to take the science and research twist on that, to what do we owe our fellow persons from which we have in superabundance? So superabundance just means we've got lots of stuff. So what do we now owe to other people? And so taking some of this, which is the first time I've used historical Catholic document in a presentation. The documentation, and the pieces in italics are what I've edited. The documentation which you withhold belongs to the hungry scientist. The code you shut away to the uninformed, and the data you bury in the earth is the redemption and freedom of the ignorant. I think that speaks a little bit to me, because we're coming from a place where we were not particularly sophisticated with how we operated, like doing great science, but not necessarily well documented. Yes, some of it was not even coded, and some of the data was not stored particularly well. So for those of you that have come from backgrounds where you've seen really useful data sets in Excel, you'll know what I'm talking about. So if I was going to resolve this, we needed to pitch a plan. So that was the first step, really. Plan's only worth its weight when you get people to buy in. So we pitched the plan. And so I had to pitch this to the GM of research at the time, who was an older gentleman. And by virtue of spending over a decade in management of science, hadn't really kept up with what was happening in the way that science was evolving. So, people were asking, what is data science? Is it just science with data? Well, we've been doing that. And so that data science term was about 10 years old when we started this journey, and thinking about the things that were new, the amount of data, and on the right there, you'll see a floppy disk, for those of you old enough to remember, which holds about 1.4 megs of data. So historically, some of our most influential multi-year, multi-million-dollar farm experiments, all the data for that would fit on a handful of floppy disks. Whereas, some of the new trials that we're working on, and we'll talk about some of the data sets later, if you might recognize that building the Burj Khalifa. So in a research experiment now, we're generating data that you would need a stack of floppy disks as tall as the Burj Khalifa to store all that data. And so that's part of the buy-in process, is to get people that really hadn't thought about how much the world had changed to think about in concrete terms what that meant. Obviously, computational capability changed a lot, and starting to think about modern workflows. And we talked about some of those yesterday with Olivia's talk. And modern techniques. If you want to apply modern techniques, you're going to have to think about these things a bit differently. So the stages of data science. So I would say probably 3 or 4 years ago, we were in maybe stage 2. So we have, parts of the business are doing data science. But really what we wanted to get to is somewhere like stage 5, where we're really reaping the benefits of it. Realistically, we're probably at about stage 4 at the moment, but that's a big leap in about 3 or 4 years with some concerted effort. And so that was about, in the start, getting people to buy into the plan. We had to talk about what is open science, and we highlighted some of the places where we would benefit. We had to introduce people to the FAIR data concepts, which everyone here is probably familiar with. and then said, what needed to happen. So if we had a 3-year vision of getting to stage 5, which we haven't achieved, but I think we've done pretty well to get to 4. We had to think about what things do we need to do at that time. So stop doing poor practice and start doing good practice, which would take some effort. The concept of going slower to go faster, but really you make back that time very quickly. And then having that commitment from the business and the management to really bed that in. So we started up the Modern Science Workflows project, and the 3 broad streams were infrastructure, skills and capability, and business disciplines. So putting that plan into action. So in terms of infrastructure, those of you that have worked with R, and so we're largely R-based, you'll be familiar with this picture from the R for Data Science book, which sort of discusses how you would go about doing data science in a general framework. And so most people start off doing that on their computer. But where do they get the data from? So one of the things that we added to the infrastructure was something that handled the versioning, discovery, sharing, and some data processing. So that's the Snowflake product. And so just as what that looks like is, being able to ingest that data and connect to APIs and get that data into our warehouse. Conceptually, we've got bronze, silver, and gold data. So like the rawish data is in bronze. Once it's been tidied up and validated, then it can move up to silver or gold. The metadata we're still working on, which will probably be through Microsoft Purview. And it's important to put good governance around that. So how do you have accounts for access? How do you manage access? Turning it on, turning it off. And just an example of the compute piece, the top one there is like working with a 4 gig data set, and it's less than a second to send that instruction up to the cloud and have it happen there and then bring the answer back, versus if you did it on your local laptop, that's taking 3 or 4 times as long. So the second piece that we added to this was, okay, what happens, so some data can, you can do aggregation, etc., in the cloud or some basic calculations. But often when you want to do simulation, etc., or detailed analysis, you need to bring it to your computer, or if your computer can't deal with it, we use POSIT Workbench, or formerly known as RStudio. So yeah, so when your laptop's on flames, as someone mentioned yesterday, we use a POSIT Workbench, and it's a pretty seamless experience. So basically, if you put your project in GitHub and it's not working on your laptop anymore, you just log into Workbench, pull down the project via GitHub, and off you go. The main difference being that we're Windows on our laptops and Linux in the cloud, but yeah, it doesn't make too much difference in the scheme of things. The third piece we added to the infrastructure was GitHub, which most of you will be familiar with, obviously, around the versioning, sharing, and reuse of code. We have to set up accounts and get the expectations right. What lives where? How do we do the discoverability and reuse? And that actually is not as good as it could be with GitHub. We're working on, I guess, inner source discovery piece. Got a couple of people working on that. And of course, you want to have best practice password storage so that your code, wherever you bring it, your passwords will still work with that code, but they're not stored in that code. And then the communication piece around when you want to share your data or analysis with other people, we use the POSIT Connect product for that. So just a few examples here. So there's an economic survey. We do an economics tracker, which is providing predictions of what we think farm performance is looking like over the next 2 seasons, and then experiment tracking. So where you've got live data coming in by API, you can do a bit of validation and you can check the reports as it comes in. which is great because, once once an experiment's finished, it's too late to go back and find out, oh, were they in paddock 15 or were they in paddock 51? It's too late, no one can remember. But to validate that data as it comes through is going to be really useful going forwards. So just an idea of what that infrastructure means in terms of being able to do analysis at scale. So yes, for our sins, a lot of work was done here historically in Excel, and it starts to become impossible to even open the files once you get into 100 meg or more, and any sort of analysis is off the table. Adding or changing to R Studio, you can get a lot more done on your desktop. If you add Snowflake, that helps you with some things in terms of viewing and processing some data, but in terms of simulation and analysis, it's adding that POSIT workbench or POSIT server piece that really gets everything humming. In terms of capability development, we've run R for data science. It's a sort of a semi-workshop style, and we've done that for 3 years, and the last 2 at Waikato University as a 1 semester paper, really targeted at our scientists and postgrad students. The thing that I like about running it through the university is it gives a formal timetable. People have to commit to it, and their managers have to commit to it, and there's assessment to check on the learning. You can integrate that into learning and development plans, so everyone's happy that that's the time that people are setting aside to improve how they work. And we had that open to other CRIs and industry. So that's worked really well for the last 3 years. But I would say that, we've basically put most of our people through that now. So for that to continue, we really need to think about, okay, who would we recruit? So that's very timely. If people want to talk to me about how we would find people that would be interested in doing that, or if there's an alternative entirely, please do get in contact, because we'll need to make a decision this year whether that course is going to run first semester next year. But it's been tremendous for our masters and PhD students. Just the way they pick it up and really get humming is very, it's incredible. In terms of business disciplines, we've got, let's see if this link here works. We've got some documentation in a book down document, if you will. So it describes, basically everything that we can smooth the transition for new people coming into the organisation about how things happen. There's a cheat sheet I've seen someone else produce that I think, we probably need a DairyNZ specific one of those. And I'd love to have a DairyNZ R package that really gets to the heart of, certain functions and certain even color palettes and graphing styles that we use. It'd be great to have that in one place. I've got some good examples, which I won't show for time today, but certainly on GitHub, we've got some good examples of how we've gone about documenting software that traditionally had just lived on one person's computer, and that one person had focused on speed rather than transparency and the ability to share that with people more widely. So step 3, what's next coming up for us? Really this continuous improvement piece. How do we maintain the momentum? And someone mentioned yesterday about celebrating the wins. If you can't celebrate the wins, you'll never be able to provide the evidence around why you need resource in this space. I think we've got a long way to go in the open science space. In some of the disciplines we work in, it's not as strong yet. Open data where appropriate. We work with Maori farming enterprises from time to time So yeah, we need to think about what does that data sovereignty piece look like, and open code. I think if we can separate the data from the code, probably more of our code could be open, because it can refer to where, for example, in our data warehouse, the data is, but without the passwords, etc., you can't access the data if it's private and we can't share it. But at the very least, the code could be open. We want to keep learning, so we have an R community that meets every 6 weeks to 2 months, and we usually have an external person come in and give us a bit of perspective about what's happening in the world. A couple of names I've discovered through this conference that I'll pass on to the coordinator for that. Yeah, as I said before, very keen to talk to people about how we would recruit for data science, or are there other options that we would look at? And I guess finally, from a big picture perspective, we'd like to link to national and international e-research initiatives. Obviously, we've got Tiara Pairangi, working away in the background. I hear that MB's sort of working on more generally what some of the future for this space might look like. And now that New Zealand is associated with the Horizons EU research funding bucket, that'll put a bit more emphasis on that international collaboration and open science, open data perspectives. So yeah, I think the future is quite exciting. Yeah, and I think the investment we've made in this space has helped us be a lot more effective. So yeah, so that's me. Thank you.
Kia ora. Thank you very much for your interesting presentation, Mark. Yes, I had a bunch of students who comes through. Nowadays, to them, the floppy disk is a save icon. They don't know what it is. They know it as a save icon. That was very intriguing for me. You've got a couple of questions, and I think we have a few minutes to answer them if you can, Mark, before lunch break.
Yep.
So I will read out the first question from George Borman. Great talk. In terms of training and building capability, have you considered creating a community of practice / self-support network?
We have people that we've sort of nominated as having the time available to help people where required. Our R community is one way of keeping track of who knows about this, who's interested in this, and through question time, etc. We can find out, oh, have you tried doing it this way, or do you need help with that? So to some extent, our R community is one of the hubs for that community of practice. Yeah, certainly if there's more ideas on how to do that more effectively, yeah, all ears.
Yep. So say that if I want to sign up for your R community, is it open for everyone, and how do we sign up for that or express interest?
Yeah, just shoot me an email and I'll pass it on to the coordinator. So yeah, we have a range of people that are interested in this from other CRIs, etc. And yeah, while it's predominantly DairyNZ people, they're people that are generally of interest in science questions, applied science questions.
Wonderful. Thank you very much. Hopefully you don't get avalanche of emails. We have another question from Olivia. Thank you, Mark. That was a great talk. Do you have any comments about data that you get as input to ensure that it is tidy? Does your training include training people that produce the data as well? Is there an
Yes.
in charge of sorting the data in Snowflake?
Right. So one of the things that we've discovered, and I did mean to mention it, that with our projects, we will probably be nominating someone as a data management person, and that will probably extend to code management. So that person will be responsible for ensuring that the data is tidy within the experiment and that it ends up in Snowflake as timely as possible. Yeah, so that's something that we're putting in place now. We have farm technical staff that are providing a whole range of data sources, etc. We're still working on how do we help them do that as easily as possible. Yeah, so we're still looking at options for that. And some of that data is geospatial in nature. So how do we get accurate location data at the time it's the data's been recorded? How do we smooth that data entry process? So yeah, there's a big historically there's been a lot of paper, and the paper around cows is not always a smart thing. So yeah.
Thank you very much. Yes, because our institute is dabbling in data generation as well. If there is a sumston.org discussion group that can feed from data scientists directly, might be a great idea. I think that's all of the current questions. But if I've missed anything, please feel free to reach out to Mark. And I think we're ready for lunch break.
Okay. Thanks, everyone.
Thank you, everyone.